Subsurface models are numerical representations of the spatial distribution of subsurface geological properties of interest such as permeability, porosity, and facies. The exploitation of subsurface natural resources requires careful and detailed planning as it is an intensive capital expenditure operation. Companies try to minimize cost while optimizing production to maximize revenue. For this, they rely on numerical three-dimensional models that predict oil reserves and daily well productions. Reservoirs are subsurface structures, sometimes several kilometers deep into the earth, of which we can only observe samples collected from drilled wells, usually many hundreds of meters or even kilometers apart. It is indeed a great challenge posed to the oil industry to use very sparse information to make crucial business decisions.
The basic purpose of modeling is to support decision-making. Models help us to predict the outcome of the decision before it's been made. In oil and gas industry, numerical models are used to make decisions about how to develop the field and to optimize reservoir development.
Numerical reservoir models are built by integrating data with different origins, resolutions, and scales. These data can represent direct measurements of the geological properties such as density, sound waves propagation, porosity, and facies. Direct measurements are sparsely located within the reservoir region and may be composed by well-logged data and laboratory experiments, as for example, Sony measurements and core flooding experiments. An important question arises when modeling geological subsurface properties: how to infer the spatial distribution of the properties of interest in between well locations. Geostatistical tools have proven their value in predicting these properties over unsampled locations, generating multiple equivalent geologically consistent subsurface models.
Predictions would always deviate from the reality because our models are not perfect. Therefore, it is important to account for uncertainty and to manage it.
Geostatistical tools also allow the assessment and evaluation of uncertainties on the inference of such properties. An additional feature of interest is the ability of geostatistical simulation tools to incorporate secondary information such as seismic reflection data. Converting seismic amplitudes into subsurface properties is commonly designated as seismic reservoir characterization.
The main challenge in this kind of studies is that we do not have direct measurements of the properties that we're interested in, for example, the pore volume or the water saturation, except for a limited number of locations where we have boreholes or core samples. However, we do have geophysical data that are acquired at the surface and are somehow related to the properties that we're interested in. We also know the physical models that link the properties that we want to model, such as porosity and water saturation, to the data that we can actually measure, for example, seismic data and electromagnetic data. So this is what we call, from a mathematical point of view, an inverse problem. We measure some data, we want to estimate some properties, and we're going to use a mathematical physical model in order to make the predictions of what these properties would look like in the subsurface. These models are generally used by reservoir engineers to make predictions about the dynamic behavior of the reservoirs in terms of fluid flow and in terms of injection and production at the well locations. The methods that we develop can be applied to hydrocarbon reservoirs, geothermal studies, CO2 sequestration studies, and near-surface geophysics and aquifer models.
Cerena have several collaborations around the globe with other universities, research centers, and companies.
One of the most active research groups in the scientific community of geostatistics and seismic reservoir characterization is certainly the Cerena group in Lisbon, Portugal. I had the opportunity to collaborate with Professor Leonardo Acevedo and Professor Amilcar Soares on the integration of rock physics models in stochastic optimization methods for seismic inversion and petrophysical inversion. Their research on stochastic methods for geophysical inverse problems is worldwide recognized, and their publications are among the most cited ones. I believe that their new book on geostatistical methods for reservoir geophysics, published by Springer in 2017, will become a reference textbook for the future generation of geoscientists. I'm very honored to collaborate with Cerena, and not only for the collaboration with the faculty, but also with the students. Student exchanges have been crucial for our research projects.
Cerena is shaping the future step by step by developing new techniques to model the subsurface towards more affordable and cleaner energy, increasing energy efficiency by improving current geomodeling workflows and providing new insights into renewable energy.